Swarm Particle Intelligence for Voltage Collapse Studies in Nigerian 330 kV Power Network. This research reports the use of a Predictive Swarm Particle Intelligence, PSPI, for the study of the Nigerian 330 kV 34 bus power system. The PSPI technique is based on a neural machine intelligence technique that follows from auditory sensation in the brain and an evolutionary technique that follows from the organization of swarming particles. The combined effect is used to determine the critical and most critical lines within the power network after being subjected to overloading faults. Using the proposed approach in voltage collapse studies shows significant implications for power system operators and managers. Keywords: auditory processing, neural machine intelligence, power networks, swarm intelligence, voltage collapse. Introduction. Presently, the Nigerian power system state shows that some regions within the more extensive high-voltage power system network still experience incessant blackouts. In certain instances, when power is available, there is a very high likelihood that a blackout may occur. In most cases, the timely determination of when the blackout situation occurs is largely unknown in the field. Thus, to overcome this lapse, power system managers should employ highly accurate and timely prediction techniques to facilitate the process. Another challenge is how best to implement voltage collapse detection/prediction solutions that can be useful as a mitigation scheme near real time. This is indeed a challenging problem that requires the determination of optimal points for each new collapse scenario presented. Existing backpropagation trained neuroswarm techniques are useful predictive optimizers, but in-depth analysis of such techniques have revealed their inherent code complexity coupled with very little or no connection to biology and recent neuroscience discoveries. See, for instance, the recent argument in Hole and Ahmed, 2019. Another obvious challenge is that of real-time integration of the existing computational techniques in real power transmission systems in the context of smart grids. In light of the challenges mentioned above, this research study aims to propose a suitable scheme and useful framework that is adaptive and accurate enough to secure the Nigerian power system network. 2. Related works. Several research works abound in voltage stability, which defines several voltage stability margins, VSMs, for use with standardized power system networks. In this research, a focus on the voltage collapse index, VCI, which describes the state of security of the power system in the presence of a possible severe contingency, is considered. Some of such related works can be found in Prasad et al., 2020, where the concept of reactive power margins has been utilized in a functional link artificial neural network, FLAN, to predict post-outage bus voltages after a series of voltage contingency selections. In their proposed model, an artificial neural network, AN, is used to predict the voltages in IEEE 14 bus power system considering different line outages and loading conditions. In contrast, fuzzy logic is used for contingency ranking of the predicted responses. Fuzzy logic, FL, reduces the misranking effect observed from the conventional bus voltage performance index, PI, using discrete linguistic data mappings. Their voltage collapse performance indices consider both voltage stability margin, VSM, and voltage deviation, VD, which used a technique earlier proposed in Dobson and LU, 1993. A set of 200 patterns have been used for neural training while 20 separate patterns are used for testing. Simulation results reported by the authors using the FLAN gave acceptable error of within 1% and an average CPU computation time of about 0.24 s. Also, the fuzzy ranking results showed that there are differences in collapse severity indices from the viewpoints of voltage deviation and voltage stability indicators. In Mannheim et al., 2019, a voltage stability margin called the L-index, Kessel and Glavitzk, 1986, is formulated into a minimization problem and integrated into a multi-objective optimal power flow solution for IEEE 30 bus power system including an active power generation source, wind power, cost and transmission power loss function. The L-index typically falls in the range of 0 to 1, and hence its minimization is very suitable for direct integration into most optimization functions. Chaotic mutation stochastic weight trade-off, SWT, the swarm intelligence technique based on non-dominated sorting particle swarm optimization, NSPSO, was then used for optimization. Using a crowding distance technique, the NSPSO is able to improve the particle selection mechanism in PSO at the non-dominated front based on a neighbor density estimate. The results of simulations in the context of voltage stability, L-index, and in comparison, with various techniques indicate that NSPSO will be the optimal one. Wu et al., 2019, proposed an innovative multi-index solution for static voltage stability analysis, SVSA, for power systems with renewable energy penetration, wind farms, in actual power grid in Hamel City, China. In their proposed multi-index solution, 6 stability indices, sub-criteria, were considered within 3 categorizations, called the primary criteria. An index weighting optimization strategy was proposed that combines subjective with objective importance weighting strategies. Here, entropy weighting, EU, was employed for objective evaluation of variations in the considered indices, and an analytic hierarchical process, AHP, based on expert opinion was used to revise the objective weighting results. Furthermore, a Lagrange conditioned extreme value, LCEV, was employed to optimize a portion of index weights assigned by the objective and subjective techniques, and a fuzzy order preference by similarity to ideal solutions, fuzzy topsis, was used for performing realistic ranking of power system voltage buses. The results of simulation using the proposed approach indicate a similarity with other methods in the literature. In particular, the authors reported a sensitivity analysis which showed variation in wind farm performance for some indices while invariant behavior was observed for others. Thus, combination of indices may be a reasonable option in order to identify power system voltage states. The phenomenon of large-scale blackouts, a situation of electrical system characterized by multiple simultaneous failure of different power subnetworks, has been investigated in Liu et al., 2018. In their studies, 51 major blackouts across the world were reviewed, then the main causes summarized. Some of the studied countries were northeastern USA, Canada, Western Australia, Barcelona in Spain, China, etc. Some of the identified causes of cascaded blackouts include the natural causes, thunderstorms, strong winds, earthquakes, tsunamis, failed equipment. Transmission line and substation equipment accounted for about 60% failure, strategic failure, lack of coordinated safety strategy, this cause is rare nowadays, and manual malfunction. Furthermore, they proposed a distributed accommodation/distributed energy within the context of energy internet, multi-energy interconnected system, to mitigate against blackouts. Such an approach encourages the use of energy hubs and alternate renewable sources of energy to support traditional grids and minimize dependency on a single source. In Dirafshian et al., 2016, a multi-objective optimization load shedding scheme for the mitigation of voltage collapse in a section of Iran power system was proposed. The optimization approach uses a novel fuzzy theta gravitational search algorithm based on optimal decision functions for securing the system. Their considered decision functions or multi-objectives are the voltage stability margin, VSM, total load cut, TLC, and integral of the deviation from nominal voltage, IDNV. Also, 6 constraints were considered for the optimal solution. They include the voltage stability, load cut, the AC power flow, active and reactive generation, branch maximum flow, and voltage magnitude constraints. Their technique was compared to 3 other similar multi-objective approaches, and they reported improved performance over these methods based on a C metric proposed earlier in Zitzler and Thiele, 1999. Garamani et al., 2018, proposed very useful special protection schemes, SBS, based on local and wide area networks, LWANs, for the Hydro-Quebec power transmission system. LWANs use telecommunication devices and phasor measurement units to support the global and local control of dynamic shunt compensators, GLCC, such as static VAR compensators, STATCOMs etc. used in maintaining the stability of the power system substation control unit, SCU. 2. Auditory machine intelligence technique. The methodology considered in this research considers the line voltage stability index, LVSI, proposed earlier in RATRA et al. 2018, the Predictive Swarm Particle Intelligence, PSPI, comprising an auditory machine intelligence, AMI, technique and a particle swarm optimization, PSO, load flow solution technique provide in subsections 3.1, 3.2, and 3.3 respectively. The combined solution is also provided in subsection 3.4. The LVSI or quadratic LVSI, QLVSI, model considers line charging capacitances and transmission line resistances. A voltage collapse contingency calculation, RATRA et al. 2018. These two parameters were previously neglected by several techniques of voltage collapse index, VCI. The QLVSI concept is as shown in Fig.1. 4. Combined system solution. In the proposed voltage collapse prediction system, a phase 1 prediction is used to perform single or one-step ahead forecasts of streaming power loads. The AMI performs this operation using the computation of a single learning formula and no specific random fine-tuning is needed to learn on the data. In phase 1 predictions, the AMI learns a sequence of data points, values, automatically/temporally in an adaptive manner such that a mean deviant point is computed as in 4. V conclusions. In this research, the promising directions of the swarming AI technique called SPIP for Swarm Particles Intelligence, combined with an emerging machine intelligence neural technique, the AMI has been presented for the case of voltage collapse studies in Nigerian 330 kV 34 bus power network. The emphasis of this was to evaluate the effectiveness of swarm predictive technique for determining the critical and most critical lines that may suffer a voltage collapse in the Nigerian power transmission system. This includes employing a swarm-based load flow solution and a neural LVSI prediction technique that improves through time or sequential expansion. The results show that using this approach, it is possible to determine the critical buses in a power network at improved accuracies depending on the number of SPIP program trial run simulations. It is also possible that there will be further improvements in prediction error accuracies and the identification of more stable line predictions as the number of trial run simulations is increased. Thus, power system operators can leverage this approach to plan ahead of any unforeseen contingency to secure the most voltage collapse critical parts of the power system network.